And this is the transmission, this is the coaxial cable. There are different kinds of coaxial cable, okay, and different structures, but for us and as a standard, for when you have a transmission line, one of the important thing for us is the characteristic impedance of the line, okay? So for the transmission line, there are three characteristic impedance, either 50 or 75 or 95 ohms. So either 50 ohm or 75 ohm or 95 ohms. For our coaxial cable that we use it in our experiment and which is available in the lab, its characteristic impedance is 50 ohm, okay? And you know what is the characteristic impedance, okay? So this is the first important thing, okay, about the transmission, about the transmission line, the characteristic impedance. The second thing, you need to know about the property of the material that is used to make this transmission line, which is the permittivity, okay? Permittivity of the material, okay, that is used in the transmission line. So the other important thing about the transmission line, about the transmission line is or let us say about our transmission line, which is coaxial cable, is the permittivity, okay, permittivity, which is epsilon r, okay, epsilon r, and when epsilon r or permittivity, it is called relative permittivity, okay, relative permittivity or epsilon r takes value between 0 and 1, okay. For our experiment today, it is 0.66, okay, 0.66, okay, because we are going to use it in our experiment. It is written in the lab, okay. So now these are the two important things, okay, the characteristic impedance and the relative permittivity. Now, what do we have in the transmission lines? In general, transmission line, we have the line will be either matched or not matched. For the matched line, that means, as we said, when you have a transmission line, there is it has characteristic impedance. If you terminate the far end of the transmission line by its characteristic impedance, then we say the line is matched. Okay? What do we mean by the word matched? This is very important. When you have line and the line is matched, that means this is TX and this is RX, and there is a transmission line here. This is the transmission line, okay? This is the generator. Signal is generated and sent, okay? Signal propagates here to the load terminal here. This is a load terminal. If it is terminated by its characteristic impedance, then there is no reflected signal back to the source. If this one load is terminated by different than characteristic impedance, or it is open or short circuit, okay, either part or all the signal, incident signal, we call it incident, or let us say transmitted signal, will be reflected back to the receiver, to the transmitter. So it is very important for us to terminate the load, to terminate the far end, okay, of the transmission line by its characteristic impedance, to avoid any reflection back to the transmitter or function generator. And we will do this in two cases. We will use this one with the termination load and without the load. And the load equals 50 ohm, because as we said, our transmission line is coaxial cable and its characteristic impedance 50 ohm. So when we want to make it matched, then we have to connect here 50 ohm. Okay? So,
can you explain that again? Like, why do we have to put it in one and remove it from the other?
Why what?
Why we have to put the 50 ohm load and then...
Because this is the line. This is for any transmission line. For any transmission line, you you have two important, as I said, two important things you have to know about them, about the transmission line. Now, the characteristic impedance and the relative permittivity. Now, the characteristic impedance is the important for us. Why? Because in the transmission line, when you transmit a signal, there is a high, because we connect load, okay, equals to the characteristic impedance of the line, and there is no reflected signal back to the transmitter or to the function generator. Otherwise, if you leave it open, the load terminal or the part terminal of the line, if you leave it open or short circuited,
We have distortion.
you will not find distortion at this terminal exactly. You will find everywhere in the line, because in this case, what do we have? We will have in the line, we will have two signals. One is transmitted, which we already transmitted, and we want to send it to the receiver side, and the other one is reflected, which comes from the receiver to the transmitter. So at any point now in the line, we will have two signals. We have the transmitted and the reflected, or we say the incident and the reflected, okay? And they will interfere. Either they will be in the same phase, and in this case the signal will be stronger, or they will be out of phase and the signal will be zero. And this is why we have something which is called standing wave ratio in the line, okay? When you have unmatched line, we will have, because now we don't have only one signal in the line. We have two signals. We have transmitted and we have reflected, and there is interference between these two signals along the line. Okay? Look here. We have function generator or a signal generator, and this device is used to generate a signal, and we will set this device to give us 10 megahertz, but our device in the lab, okay, cannot generate 10 megahertz. The maximum frequency that we can get it is 1 megahertz. We will see it in the video. I think 1 megahertz, yes. So we will use that frequency. Okay? No, sorry, not this one. This one, okay, we have 10 megahertz and 2 volt peak to peak, and I show you that in the video, and I show you if you watch the video, the function generator. Now the signal is generated here and is sent through this coaxial cable. This is the coax L1, okay? Is sent through L1 to the channel 2 oscilloscope, and in the oscilloscope channel 2, I want to like tap the signal, take part from the signal. So I will put T junction, and the T junction is not more than like this, okay? This like this, and this is connected to the scope, and you can take, this is the signal from the function generator. This one goes to the scope, and this one you can get it wherever you want. And what we do, you take part this one through another cable, which is L2, and we connect this one to channel 1. To channel 1, and also in channel 1 we will put T junction, because I want to terminate the load, terminate the line by its characteristic impedance, which is this 50 ohm. So now this configuration here, we have source, we have transmission line, another transmission line, and at the end, at the far end, where is the receiver, we terminate the load by, we terminate the line by its characteristic impedance. So this is the case of matched of the matched filter, of the matched line. Now the line is totally matched because the far end, okay, is terminated by the characteristic impedance of the line. This line, as we said in the lab, our coaxial cable, its characteristic impedance 50 ohm. Okay, guys. So here is the idea. What we will have Now, we have a signal generated here. This signal propagates through this cable to this terminal, and now it displayed on channel 2, okay, which is the blue signal. Then the signal propagates again through L2 to channel 1, and at channel 1 we have termination here by the characteristic impedance, so there is no reflection. All the signal transmitted will be delivered to the load, no reflection, okay, which is the best case, okay. So what happens here, we have another signal here, which is the yellow one in the scope. The only thing that now we are suffering from it for our experiment, okay, we don't have the problem of reflection because the line is terminated with its characteristic impedance. The line is matched. The scientific term that we use it, we say the line is matched. Matched means you terminate the load by its characteristic impedance. The problem, only problem for us now, there are many problems, but for us now, the problem is the delay. The delay propagation time that is one of the important factors should be considered in your experiment. Now the signal on channel 2 here is, this signal is propagated, or it propagates, sorry, through the L1 only, okay, only L1. But the signal here in channel 2 propagates in L1, okay, and L2. In other words, if we compare the signal between these two channels, channel 1 and channel 2, if we take channel 2 as a reference, okay, the signal here, then the channel 1 receives the signal after a short delay, because the signal from channel 1, from channel 2 should propagate in this cable, okay, until it reaches the channel 1. So we have a delay. Okay, it's a very short delay, nanosecond, but there is a delay. And you can imagine when you have a cable under the ocean between two countries, or any under the ocean, for example, how long it. So in this case, you can make an estimation about the delay. So the delay is an important factor. Okay, and most of the problems, okay, comes from the delay. So now what we will see on the scope, we will see the signal on channel 1, channel 2 and channel 2, channel 1 and channel 2, but there is a delay between them. There is a delay between them. Now, I don't know if okay, this is an experiment with 3 transmission lines. Okay, function generator, guys. This is the function generator. We use it in the lab, and here we have square wave. Okay, we can use any signal. Here we have square wave, and we define the frequency 10 megahertz, amplitude 2 volt peak to peak, 0 offset, 0 phase. We don't want any. We don't need the offset, and you know what is offset? Offset, you push it up or down, give DC level to the signal, and the phase, you shift it left or right. This is the phase. So both of them is shifting. This one up and down, and this one left and right. So this is the source, function generator. Now here, this is the coaxial cable. Okay, here the coaxial cable, and we connect it to the channel 1 of the function generator. Okay, this one now should go to the channel 2 in the scope. Here is it. Okay, here. This one, this comes from the function generator, I guess this one from the function generator, and this is the T junction here. Okay, it's connected to the channel 2 here, and this one here, we take it and connect it here to the channel 1. Okay, again, this is T junction here. This is the coaxial cable, which is L2 in our lab manual. and this is the load. This is the load, which is the 50 ohm characteristic impedance of the load, of the cable. So here,
so we have here, we have
this
T
one,
junction.
this is
And
T
then
junction.
the other terminal of T junction, we connect this one. This is 50 ohm load. Okay, so this is the characteristic impedance of our transmission line. This transmission line coaxial cable is characteristic impedance 50 ohm. So we terminated it at the end, at the load side by 50 ohm. So now the line is matched. The line is matched to its terminal.
Line is matched means no reflection. We don't have reflection, which is very important for us. There is no reflection, there is no signal reflected back from the load to the transmitter side. So now we have, as I said, we have the problem of delay, or there is a propagation time. And here the signals, here the two signals. Okay. Here are the two signals. The blue one, channel 2, and the yellow one, channel 1. Okay, and we see they should be constant, but now there is a delay between them, like here. Okay, this is the delay, this is the delay. Okay, and that delay because of the transmission line. Okay, because the signal is carried or propagate, the signal propagates in transmission line. This is physical medium, so we will expect there is a delay, and the delay is here. The delay is here, which is minus. Minus, we don't use it. Minus, this is just when we choose here the options to compute the delay in the scope. It says to you, you want it from this one to this one, or from this one to this one. So there is a minus. For us, it is time, delay time, so absolute value. We don't have negative delay. Okay? So absolute, it is 8.4 nanosecond.
Because here there is delay between the two signals, because one signal is not in the second two cables.
Okay.
The delay.
This is the delay.
See it?
That you will use it. Okay?
Delay between one.
This is the delay that you will use it. Okay? Now I will go back to the slide. Here. So now we have the signal generated, sent to channel 1, channel 2, and we have two signals on the scope, and there is a delay. Now what we are going to do, we are going to estimate the cable length L2 based on this delay. Okay, based on the delay between the two signals, and which is very simple. Okay, don't forget to answer these questions. Okay, and when you answer the question, please write the question, type it also. Okay, in your report, and under the question write the answer. Okay, and most of these questions I explain it now to you. Here, as you know, the cable, first of all, when we have a transmission line, the speed of the signal, the propagation speed of the signal in the transmission line equals to this is standard, equals to the speed of the light in the free space, C, which is 3 times 10 to power 8 meter per second, 3 times 10 to power 8, divided by square root of epsilon r, mu epsilon actually, but mu epsilon is constant now, we consider it, so divided by square root of relative permittivity. Okay, so this term here, C divided by epsilon r, this term is the speed of the signal in the transmission line. Speed of the signal in the transmission line. Now, speed in mechanics, what is speed? Speed is for example, the speed is distance per time. Distance per time, right? So when you multiply the speed by time, you will get the distance, which is the length here. This is a simple formula from physics, right? So this is the speed of the signal, okay, in the transmission line, okay? Since we are not, if we do it, for example, this is in the free space, then we don't, this one will be 1 epsilon r, and the signal at that time propagates at light speed. But now we have transmission line, and this has a properties, okay? So this is the speed of the signal, okay, and we multiply it by the delay, which is time. Remember the speed, even in the car, when you drive a car, the speed is, for example, meter per second. When we multiply it by time, okay, time with the time cancel, we will have only the distance, which is the length of the cable. So when you put the delay, which you got it, and in this experiment, our transmission line was matched, okay? Now we will try to find it, what the case if it is it is not matched, unmatched case. In the unmatched case also we can't find it. We can't find the length of the cable, okay? So now this is the first calculation you need to do it. Don't forget, answer all the questions and compute this one and put it in your report. C is the speed of the light in the free space, which is 3 times. It is 2.99 something, but we say it is 3 times 10 to power 8 meter per second. Epsilon r, relative permittivity given here at the end of the report, which is 0.66. Okay, we have a cable. This cable is RG58, and RG58 has the material, its relative permittivity is 0.6.
Should be 2.3, right?
Sorry?
Should be 2.3 under the square root.
Yeah, you can't put it 2.2 over 3. This 1.66, put it here. If you want this one to write it like a numerator, it will be 2 over 3. But use it 0.66 and put it in the calculator.
Okay.
Okay, guys, this is part 1. Now we go to part 2. Okay? In part 2, we have 3 parts.